All right, just a couple more things that we got to talk about before you're let loose to your final studying session and then your final test that you're going to take that is going to prove to you once and for all that you will, in fact, pass this test. So we're definitely going to be looking for some high scores by this point on that test, or something has gone incredibly wrong. You may want to reach out, contact me, or you may want to start back over if you know there's particular areas that you're really struggling with at this point. But hopefully you're going to do a little study after this video. You're going to do that final test and you're going to be scoring way in the high 80s or low 90s or even maybe the high 90s. And you're going to be killing it, and it's going to indicate to you that it is time to go take that FAA test. But right now we're going to talk about load performance. I'm using the old load performance piece that I used to include in my regular trainings, which included this loading graph. I no longer use that, but we're going to get into talking about the gross takeoff weight of an aircraft and how that affects stall speed. Gross takeoff weight is the weight of the aircraft plus anything and everything that's attached to it or that it's pulling around. The heavier the aircraft is, obviously, the higher the stall speed is going to be. And we're going to talk about stalls more importantly here in just a little bit. But the more you put on something, think about it. Like in a manned aircraft, piloted airplane, when you've been on a big jet airplane and it has to get rolling and it has to get up to a certain speed before enough lift is created for that aircraft to get off the ground, you know that if it slows down any, it may fall out of the sky, right? So you want it to be faster. The more weight you throw on that aircraft, the faster it's going to have to be in order to keep it aloft. If the stall speed increases, that means it'll stall at a higher speed. So that means you have to be going even faster to keep it in the air. Well, when you start doing anything other than straight and level flight, you're creating new gravity forces on that aircraft and the weight that the aircraft is feeling. So we talk about these as G's. You've heard about these when people are talking about aerobatic flight, and they can be experiencing 6, 7, 8 Gs or more. That is the load factor, basically, that you're feeling from the aircraft doing different maneuvers. And again, the only time that it's the same as 1G is when you're in perfectly straight and level flight. If you're going up or you're going down, you're turning side to side, those load factors are going up. They can even go into the negative numbers, and you can have less than the gravity of the Earth. But we're only going to talk for the benefit of the test about positive Gs. So the way you're going to answer the question on the test, it's going to ask you a question like, you've got an aircraft that weighs 30 pounds and you're in a 45-degree banking turn. Well, they're going to give you a calculator and a pencil and a paper. I suggest you use them on the test. If they go to give them to you, do not turn them down. Take those, because this is going to help here. As you can see, when you look down the little table here on the left side of this chart, you see the angle of bank and you see the load factor. So the angle of bank is 45 degrees. Your aircraft weighs 30 pounds. They're giving you the load factor of 1.414. That is your coefficient. Coefficient is a number you multiply things by. In this case, you're going to multiply that 30, your weight or your gross weight, takeoff weight of your aircraft, times the 1.414, and you're going to come up with an answer. And let me tell you this about the answers that you're going to find on the test. They're going to give you 3 possible answers. And each one of those 3 possible answers, there's going to, each time they give you a set of answers for a question like this, there's going to be 2 answers that are going to be kind of far off. And there's going to be one answer that's not going to be perfectly what you came up with in the calculator, but it will be if you were to round it, or it's going to be relatively close to what you would come up with if you round it. The important thing is to know they're not going to be exact figures. They never are If you get one that's the exact figure that you came up with mathematically, it's a strange occurrence. Not saying it couldn't happen, but usually when I've done it, my calculations are a few tenths or maybe a half a pound or a full pound off from whatever they say. Go with the one that is the closest to what you come up with. The 60-degree banking turn is the best because it's exactly 2 times whatever your gravity is. And if it's 2 times the gravity, then you could take the weight, like the 30, and say, well, now it weighs 60. Likewise, if you were in a piloted aircraft and you were the pilot on board and you weighed 150 pounds, you turn into a 60-degree bank angle and you now feel like you weigh 150 pounds, 300 pounds now. Because you just take your weight, multiply it by the 2. Now, do you literally weigh that much? Yeah, sort of. But it's more like, you didn't gain any mass in the plane. It's just that the gravity now, the gravitational pull, the factor, the load factor is now changed. So it's not like you've gained weight or anything, but it feels like you have. So anyhow, that's important to know because when you read your manufacturer's information about your aircraft, it's going to tell you what the stall speed is for different weights and that kind of stuff. So you want to definitely know it. Over here on the right, you see the load factor chart. That's nowhere near as good as your table over here to the left because the table actually gives you the load factors and the coefficient you're going to multiply by. It's much harder to try to judge it by the graph over here, but you can see anything past 60 degrees goes up very quickly. And that's basically what this chart's trying to tell you. I'm not going to go over this second chart, so we're just going to pass by it. And we're going to talk right into stalls. Talk about angle of attack, and we're going to talk about critical angle of attack. And so the angle of attack, you have to know that there's this invisible line that goes down the center of the wing or the airfoil from the front to the back. And that's called the chord line. And then you have a relative wind, which is the direction that the wind is coming toward the aircraft or the airfoil. And you need to know that lift is a function of the density of the air, first and foremost. The density of the air is by far the most important thing. Then, of course, how fast you're going through that air, the amount of wing area you have, and then this angle of attack is going to be very significant to that. That is what you need to know there. Then, the critical angle of attack. Under normal circumstances, the wind would be coming at your wing and kind of hugging it, top and bottom. There's this principle called Bernoulli's principle, which says that if a fluid is going faster, it has a lower pressure. If a fluid is going slower, it has a higher pressure. The way that affects an aircraft is that they say that the wind that is going over the top of the wing is flying or going faster over that wing than is going across the bottom, just by virtue of how fast, or how far rather, that air has to travel and get there at the same time. So Bernoulli says it's creating a lower pressure above the wing, and then that means that the higher pressure air is wanting to try to push towards that lower pressure, because that's how high and low pressures act in nature, is that high pressure tries to move toward low pressure. And when that happens, you're going to get this nice cushion of air, this upward push on the bottom of the wing to try to keep that up. You're going to have sort of a suction on the top of the wing, and that's how you want things to be. But when you start pulling that wing back to gain altitude, it's going to, cause your aircraft to fly a little bit slower, and it's going to cause this wind that's going over the top of your wing to eventually separate from the wing. And when that happens, it's called the critical angle of attack. That wind separates and you get some turbulent air going on over the top of that wing. And that's when it goes into a stalled configuration. You may have thought before that stall meant that the engine stalled or quit. When they talk about stalls on aircraft, they're more talking about the stall of the wing. When the wing can no longer fly, it's going to fall from the sky. And that's the bottom line. And this is how it happens. So when you see questions in reference to when does a plane stall, it stalls at the critical angle of attack. There is always a particular angle of attack that is the critical angle of attack. No matter how fast or slow an aircraft is flying, when you hit critical angle of attack, that aircraft is going to stall because the wind, the relative wind, will separate from the aircraft wing. And that is the end of that story. So that also concludes everything we're going to be giving to you in the video sessions. I'm going to have one more brief video to discuss next steps, and be looking for that. And until then, finish that studying, do your last bit of studying in your book, and then go hunt down these items on physics, physiology, and safety, and the things that we've been talking about. And then go take your last test. And when you take your last test, again, you should be scoring well. If you're not, something went wrong. I'd love to know more about that. Please get in touch with me and give me your feedback if you think that that something about the program could have changed to make things better for you. I'd love to hear it. But until then, go take that test and then go get that FAA test done. And I'd love to hear back how you did on that as well. Till then, happy studying.